In this video, we are going to talk about vector fields. We'll go through all of these main points which are contained on this slide first, and then we'll go through each individual point in more detail with more examples. We'll start with the definition of a vector field on Rn. So a vector field is a map from Rn to Rn, and it assigns to each point x in its domain a vector. Graphically, we can picture f as attaching an arrow to each point. So for every point in Rn, we're going to associate a vector, and generally that vector, we draw it originating at x rather than at the origin. Then if we have a map that assigns a number instead of a vector to each point, that would be called a scalar field. And again, what we do is we draw the arrow, the vector that's assigned for each point x, with its start at x rather than at the origin. And we'll see some examples. Examples of a vector field include fluid moving through a pipe, such as this illustration here. So at this point, we associate this vector, and at this point, we associate this vector. So at each point, we associate the vector representing the fluid velocity at that point. And that will give us the velocity field v of the fluid. Note that the length of the arrows, the speed as well as the direction of the flow can change from point to point. So here, it's the length of the arrows or the speed that's changing, whereas here, the actual velocity, because the direction is also changing. Our next example is the rotary motion, such as the motion of particles on a record player, and it's described by the vector field v, which assigns to every point xy the point negative y x. And what you get is this motion, this vector field here. And we'll look at this more in detail, but just to give you an example of one point, let's say x is equal to 1 and y is equal to 0. That's this point here. X is 1, y is equal to 0. That'll associate the point negative 0, 1, or 0, 1. So that's the vector that points in the direction of 1 unit in the direction of y. So this vector is the one that's associated with the point 1, 0. And then we can do multiple points and get this vector field here. The next example is the force of attraction of the Earth on a mass m, and that can be described by a vector field on R3, the gravitational force field. So according to Newton's law, this field is given by, so for every point x, y, and z, we get the minus little mass m times the Earth's mass m times gravitational constant over r cubed. So, and then we have the x, y, and z direction. So then what we get is, as we get closer to the Earth, the magnitude's larger, and as r gets bigger, the radius farther away we get out, the magnitude of our vectors gets smaller, but the vectors all point in towards the Earth. And f is also a gradient field, which we'll talk about in a minute. The fourth example is the velocity field approximating water in a circular motion, such as occurs when you pull the plug in a tub of water. So kind of this here, the water sort of circulating around this point. And the equation for that is y over x squared plus y squared. And then for the next coordinate, minus x over x squared plus y squared. It just so happens for the gravitational force of attraction, the vector field given by f over here ends up being the del operator, the gradient of this function here. So in general, vector fields need not be a gradient field. That is, the vector field need not be the gradient of a real valued function like the gravitational attraction. So this just happens to be, f just happens to be the gradient of another function. But in general, that's not the case. But if it happens that it is, then this function here, whose gradient gives you f, is called the potential function for the vector field f. Now that we've talked about vector fields, we can talk about flow lines. So if f is a vector field, a flow line for f is a path, sigma. Remember, we talked about paths in chapter 2. and the paths were denoted with a sigma of t. T was the time, and sigma was sort of like the position of some particle at time t. And if you follow the path over time, then you get sigma, the path. So a flow line is a path. It's a sigma such that the derivative of sigma, sigma prime of t, this is also the velocity, is equal to f of sigma of t. So when you plug a path into f, you get its derivative, or you get its velocity. Another way of saying this is f yields the velocity field of the path. Plug in the path, you get the velocity. Geometrically, the problem of finding a flow line at a given point, x naught, for a given vector field is that of threading a curve through the vector field in such a way that the tangent vector of the curve coincides with the vector field as in the figure. So here I have this vector field given by the arrows. This is my flow line, and as you can see, whenever it touches a vector, it touches it tangentially, or at least that's what I meant to draw. Analytically, the problem of finding a flow line involves solving the differential equation with an initial condition. And the differential equation is here, just from the definition of your flow line. Sigma prime of t is equal to f composed of t, and our initial condition is sigma of 0 is equal to x naught. We could break down our sigma of t into sigma gives us our xy coordinate, so sigma prime of t is x prime of t, y prime of t, z prime of t. Our function f, our vector field. So for example here, we have a function that gives us the first coordinate of our vector field, a function that gives us the second coordinate of our vector field, and the function f3 that gives us the third coordinate of our vector field. So we can break up f into f1, f2, f3, so that our derivative of our first component of our velocity is equal to f1 of x1, y, and z. So this is just an expression, the same expression of this, except sigma is broken up into, or sigma prime of t is broken up into x of t, y of t, and z of t, and then our f is broken up into f1, f2, f3. And we have this example here, which I don't have room to do the problem, except we will do it in our video. A vector field is a map. It goes from Rn to Rn. So for every point in its domain being Rn, it will assign a vector. Graphically, we may picture f as attaching an arrow to each point. So for example, if we associate with the point 1, 2, the vector 4, 3, then here is point 1, 2. Here's our vector 1, 2, 3, 4, 1, 2, 3, 4, 3. So what we would do is we take this vector 4, 3 and we position it at the point 1, 2. So this is how we represent f of 1, 2 is equal to 4, 3. If that vector actually happens to be a scalar, then that map is called a scalar field. It is convenient to draw the arrow representing f with its foot at x rather than at the origin, which is exactly what we did in our example. We took the vector and we moved it to 1, 2. The last thing I want to talk about is a scalar field. That's a map that assigns a number to each point rather than a vector, and I have an example here, versus a vector field, which assigns a vector to each number. So here you can see my vector field, xy. It takes two inputs, xy. My scalar field also takes two inputs, xy, but my vector field takes this xy and produces a vector, whereas my scalar field takes xy and produces a number, a scalar, not a vector. It only has magnitude. So if I plug in 1, 2 into my vector field, I get the vector 2, 3. When I plug in 1, 2 into my scalar field, I get the number 5. When we graph this vector from my scalar field, I take my vector 2, 3 and I move it to 1, 2. So this is how I express this vector field. So at 1, 2, the point 1, 2, I have my vector 2, 3. Whereas for my scalar field at 1, 2, I just associate the number 5 with the number 1, 2. Next, we are going to go through our 4 examples. The first example is fluid moving through a pipe. At each point, we're going to associate the fluid velocity at that point. So we obtain a velocity field V of the fluid. I think I missed some words here. But anyway, so looking at this picture, we have kind of a pipe, and then it kind of gets funneled, whatever fluid gets funneled through, and it comes out through this other pipe. So the idea here is you see at this point, the fluid is all moving in this direction, and it's moving with some speed over here. Whereas here, it's still moving pretty much in the same direction. However, you can see because the magnitude of the vector is longer, that now at this point, it's speeding up. Here you see the fluid is slowing down, as indicated by the shorter vectors, but also the direction, everything's sort of changing direction. So here the fluid is changing directions at this point, and this point. And then by the time we get to this point, it's speeding up and it's gone back into the original direction. Here and here, it's still in the same direction, but starting to slow down again. So the length of the arrows indicate the speed, as well as the direction. And both the length, the speed, and the direction can change from point to point. Our next example is rotary motion, such as the motion of particles on a record player, and it's described by the vector field V of xy. So the vector field V associates with xy the vector negative yx. I have the diagram of it here for you. However, this is a little bit complicated, so I'm going to draw this diagram step by step. Over here, I've put some points xy, some easy points like 1, 0, negative 1, 0, 0, 1, 0, negative 1, and then V associates this with negative yx. So over here, I put negative y, so 0, 0, this 0 goes to this 0, this 1 goes to negative 1, this negative 1 goes to positive 1, and over here I just copied over my x's. I'm going to start by looking at what happens at the point x equals 1, and y equals 0. So that's this point here, right here. And the vector looks like 0, 1. And so the vector 0, 1 is, it's at x equals 0, y equals 1. So it's this vector here. So next, I'm going to move this vector over to the point 1, 0. Next, I have at the point minus 1, 0, that's this point over here. I'm going to draw the vector 0, minus 1. So that's 0 and 1 unit in the negative y direction. So I'm going to move this vector over to my vector 0, minus 1, over to the point minus 1, 0. Similarly, at the point x equals 0, y equals 1, that's this point here, I am going to have the vector that points in the negative 1 x direction at y equals 0. So in the negative 1 x direction at y equals 0. But I need to move this vector over to this point. So here I'm going to move that vector. And last, at the point 0, negative 1, x equals 0, y equals negative 1, I need the vector in the positive x direction in the and 0 y direction. So that's this vector here. That's my 1, 0 vector, but I need to move it to the point 0, minus 1. This is the start of my graph, and that's this arrow, this arrow, this arrow, and this arrow in this graph. Next, I'm going to look at the point x equals 1, y equals 1. That's this point here. And this vector that belongs there points in the minus x direction 1 unit and the positive direction x units. That is this vector here in the negative x direction 1 unit, over here, and in the positive y direction 1 unit, and this vector needs to be moved to this point. The next point, I just decided to take this point here at the end of this arrow, which is the point x equals 0, y equals 2. I plug it in and I get negative 2, 0. So I'm in the negative 2 direction. along the x-axis and 0 along the y-axis. So when I move that over, it's going to look like this vector here. And next, I'm going to take this point, the endpoint of this, as my next point. So this is -2 in the x direction and +2 in the y direction. When I plug it in, I'm going to get the point -2, 2. And I'm sorry, this should be -2, -2, because it's -y, and then x, which is -2. So over here at this point, I get something that points in the -2, -2 direction. So -2, -2, it's this vector here, which I am going to move up to this point. And you can see what I'm starting to get is this spiral. It starts at x equals 1, y equals 0. Here, you can see I'm starting to get this spiral now. You can continue this process, taking this point, plugging it in, getting the next vector going down. Also, you can start over here with this start, and you will get this spiral over here. Or you can start at this point. What would this be? -1, -1. Where's my, and you'll get this spiral. Essentially, what you'll see is this rotary motion. To get some further intuition on our rotary motion, we can look at the absolute value of v. And we notice that's going to be x squared plus y squared square rooted, which is equal to r, which means v has a constant length on a unit circle of radius r. So in other words here, if I look at the unit circle, radius equals 1, you can see all my vectors have a length of 1, right? So for when I'm on this circle, those are all of these points here, radius 1, you can see all of these vectors have length of 1. Similarly, when I'm out at a circle of radius 2, you can see that all my vectors then, well, I only have one vector of radius 2. Do I have another one? If you calculated this one will also, is this? Yeah, this should be radius 2. These two vectors will have the same length. The other thing, that tells us about the length of the vectors. As for where the vectors are pointing to, you can look at point xy when you dot xy with v. So if I dot this xy with my v, so I get xy dot minus yx, that will be equal to 0. That means because the dot product is equal to 0, and remember the dot product of, so v dot w is equal to the magnitude of v, magnitude of w, times cosine of the angle theta between v and w. If the dot product is equal to 0, that must mean the cosine is 90 degrees. In other words, v is perpendicular to the position vector. And you can look at this and you can see that at the 1, 0, you can see the vector for our velocity is perpendicular. Over here at -1, 0, maybe this is boring, the velocity vector is also perpendicular. If we want to look at 1, 1, that's this point here. So our 1, 1 vector is this blue line, and you can see the velocity vector is our -1, 1 vector. So it's this line, and again, it's perpendicular. So as far as length of it, it's basically this same length on a unit circle, and as for direction, it's always perpendicular. V is perpendicular to the positional vector. This is a very common example to have in problems on exams, so it's worth knowing. Our next example is the force of attraction of the Earth on a mass m. And this is the gravitational force field predicted by Newton's law. And the field itself is f of xyz is equal to -m, that's the mass of the small mass that's being attracted, capital M, which is the mass of the Earth, times g, gravitation of the Earth, over r cubed, that's the radius from the Earth's center, times x, this is the x direction. In the y direction, we have the same, minus m, capital M, g, over r cubed times y. And for the z direction, we have minus m, capital G, over r cubed times z. And again, r is the radius from the center of the Earth. So that's the square root of x squared plus y squared plus z squared. Here is the drawing. You can see sort of as we're closer, these vectors that are closer to the Earth have a longer line than these vectors out here that are a little bit further away. So those vectors should be shorter. In other words, the force of attraction is greater, the gravitational force is greater as we're closer to the Earth. And you can see that's going to be true from the formula because you're dividing by r cubed. So the bigger the distance from the Earth, the bigger the r, the smaller the force of attraction. The other thing to know is this force here is actually a gradient field. So this vector is a gradient field. In other words, f is equal to the del, the gradient of some other function. And the function it's a gradient of is negative m, capital M, g over r. And to see that, we can take the del, the gradient of this function here. So I expanded r into x squared plus y squared plus z squared raised to the 1/2. And now I was going to do del, except one thing to simplify things, this m, g, these are just constants. So I'm going to pull them out, and I'm just going to compute the partial derivative with respect to x of the denominator, the x squared plus y squared plus z squared to the 1/2. And since the gradient, since this looks symmetric in x, y, z, and the gradient is dx, dy, dz, my dy, dz are essentially symmetric to the d dx case. So I did the derivative of the denominator, just pulling out the constants here for a minute. So the derivative with respect to x of this, I rewrote the denominator as x squared plus y squared plus z squared to the negative 1/2. So when I take the derivative, I can have my minus 1/2, my 2x, and then my x squared plus y squared plus z squared to the negative 3/2. In other words, that's going to be my negative x over r cubed. Again, r is the square root of x squared, y squared, z squared. So putting then with this, my constant, that means my first coordinate of my f is going to be negative little m capital Mg over r cubed times x. And then I said by symmetry, y will look like this and z will look like this. And what you can see is this is exactly equal to f. So f is the gradient of this function here. Then we will call, by this definition here, we will call this, the minus m capital Mg over r, the potential function for the vector field f. Our last example of a vector field is this velocity vector field that approximates water in a circular motion such that occurs when you pull the plug out of a tub of water. This is my wonderful illustration. So you have this tub, you pull the plug and the water's draining out and the water's kind of circulating around this center. And the equation that approximates this circular motion is v of xy is equal to y over x squared plus y squared. And the second coordinate is minus x squared plus y squared. Again, this is a common example. I had mentioned for the gravitational force of attraction that f was actually a gradient field. In other words, f was the gradient of some other function. And I said that little function, this function here, was called the potential function. In general, a vector field need not be a gradient field. That is, a vector field need not be gradient of a real valued function. But if f is the gradient of some function f, then f is called the potential function as we had identified here. Now that we've talked about vector fields, we can talk about flow lines for a vector field. So a flow line is a path such that the derivative of the path is equal to f of the path. That is, f, when you plug in your sigma of t, your path, you will get the velocity. And again, what that means is f yields the velocity field of the path. You plug in the path, you get back the velocity. Geometrically, the problem of finding a flow line to a given point x naught for a given vector field is that of threading a curve through the vector field in such a way that the tangent vector of the curve coincides with the vector field, as in this figure. We'll take a closer look at that. Geometrically, the problem of finding a flow line at a given point x naught for a given vector field f is that of threading a curve through the vector field in such a way that the tangent vector of the curve coincides with the vector field as in the figure. So here I have my my vector field. So those are the arrows. When I want to do this flow line, this black curve here, what I'm going to do is kind of go through my vector field, and whenever I see a vector, I'm going to try to change the shape of my flow line so that it's just tangential to the vector. I come over here, I hit another vector, so I'm trying to be tangential to this vector. I flow, and it changes the direction, and I flow until I get to another vector, and I need to change my direction so it's tangential to this vector. Analytically, you're going to solve this set of differential equations. I have cleared out some space. I have the definition of the flow line here, which I'll just underline here. And then what else do I have? This description of the geometry, which we're not going to look at anymore, and the analytic problem of finding the flow line is solving these differential equations. So I'm going to look at this kind of exam or definition, sort of piece by piece, and at the same time we're going to use this example to illustrate as well. I moved my definition of the flow line here just so that I can kind of see it easily, and then in the definition we just talked about a flow line as a path. We didn't actually specify like it's sigma of t, so it's a function of t. It's parameterized by t. Often we think of time, and sigma gives us an x, y, z coordinate if it's in 3 dimensions. If it's 2, it gives us an x, y coordinate. Its position at time t. Let's see, what else do we have? So in our example, our sigma of t is equal to t squared 2t minus 1 t to the 1/2. So we can think of time as -1. That will give us a complex number I. Maybe we don't want to do this because we already have 3. We're already in 3 space. We don't need to add the complex numbers in there as well. So let's start with t equals 0. So here we'll have 0, minus 1, 0. When t equals 1, we're going to have 1, 2, minus 1 is 1, and then 1. When t equals 2, we'll have 4, 4 minus 1 is 3, and then square root of 2. When we plug in 3, we're going to have 9, 6 minus 1 is 5, and then square root of 3. So you could plot these in 3 space if you'd like, and you'll get a path, and you can see as t progresses from 0 to 3 what that path looks like. I'm not going to graph that because I'm too lazy to graph this in 3 space. Now I can take my sigma prime of t, which is going to be x prime of t, y prime of t, z of t. For my example, I'm going to have 2t, 2, and 1/2 t to the minus 1/2. Next, we're going to talk about a vector field, right? We talk about a vector field. We have this vector field here. We say f yields the velocity of the path. So let's denote our vector field f of x, y, z. And f is a function f1 that gives us the first coordinate of our x, y, z transform. f2 gives us the second coordinate of our vector field, and f3 gives our third coordinate. So for example, this sounds kind of strange, but for example, in our example problem here, our vector field is equal to y plus 1, 2, and 1 over 2z. So f1 is the function that gives us our x coordinate, y plus 1. f2 is the function that gives us our y coordinate, and f3 is the function, 1 over 2z, that gives us our z coordinate. So it kind of looks a little better with this example. To finish our example, if sigma is a flow line of f, and our example f was given by y plus 1 to 1 over 2z, then our sigma prime of t should equal to f composed of sigma. That's just from our definition here of a flow line. So we have our sigma prime of t here. So now I need to do my f composed of sigma of t. So my f composed of t, first I need y plus 1. My y is my t minus 1, and then plus 1. Where else do I have f? F, then I have 2, and then I have 1 over 2 times z. So that's 1 over 2, and z is equal to t to the 1/2. So this will just give me 2t 2 and 1/2 t to the minus 1/2, which is exactly equal to sigma prime. So here I have shown that sigma of t is a flow line for this vector field F. On this side, I went ahead and plugged in F composed of t, and that's equivalent to plugging in sigma, plugging in sigma into F is equivalent to plugging in sigma in the function that gives you x, the function that gives you y, and the function that gives you z. And the reason why I did this is because I wanted to compare this line here. This is how to find a flow line over here. So the problem was to find a flow line, finding a flow line. Our example was actually easier because it was just to show, it gave you the flow line and it asked you to show it's a flow line. So we only had to show that this condition held. If we wanted to actually find the flow line though, what we would be doing is showing this F1 composed of sigma of t is equal to our derivative. So in other words, it's this line here. Our x prime of t, our derivative, is equal to f composed to sigma of t. And here instead of sigma of t, we just wrote sigma of t in terms of x, y, and z. So that's what this is here. And then we have to show that our second component, y prime of t, is equal to f sigma of t. So that would be f, and then our sigma of t just taking this form here. And then our z prime of t has to equal f3 of sigma of t. And that's this last component here. So that would be 3 differential equations that you would have to solve. But a lot of people take vector calc before they take differential equations. So it's good to know that this is the system you would have to solve, but we're not going to do an example solving this equation. To review what we have discussed in this video, we talked about vector fields, and we said a vector field was a map from Rn, so it takes a bunch of points in n space, and then it gives you a vector in n space. And graphically, we picture F as attaching an arrow, this vector here, that we end up with, at each point over here from the domain. So a map that assigns a number to each point is called a scalar field. If instead we're at R1, then that would be a scalar field. The examples we had were a fluid moving through a pipe. We had this rotary motion that was given by this vector field v of xy is equal to negative yx, so it just kind of swaps the x's and y's and puts a negative in front of the first coordinate. And this is a very common example, so you can kind of want to be familiar with this. The other, another example we had was the force of attraction given by Newton's law here. And this was an interesting example because f was actually the gradient of another function. It was the gradient of negative little m, capital G over r. And then our fourth example was the velocity vector field approximating water in a circular motion, such as what occurs when you pull the plug in a tub of water. And that was given by this equation here, also a very common example. V of xy is equal to y over x squared plus y squared, and then minus x over x squared plus y squared. We talked about here, in the case, so it's not always the case that a vector field is a gradient field. In other words, the vector field is not always the gradient of some other function like this gravitational field is. However, when it is, then this function, that's the gradient, that we take the gradient to get, is called a potential function. The next thing we talked about was a flow line for f, and that was a path such that the derivative of the path is equal to the field composed with f. And we did an example of that. We talked about what it looks like graphically, and we did an example to show that a particular path was a flow line of a particular vector field. The actual problem of finding flow lines involves solving these differential equations, and we kind of briefly talked about that as well. For review, I have these 3 problems. The first is sketch the vector field of f going from R2 to R2, where f of x is equal to a, and a is a constant vector. 2 is to calculate the flow lines of the constant vector field f of x, y, z is equal to 2, minus 3, and 1. And last is set up the equations for the flow lines of f of x, y is equal to minus y, x. My suggestion is to pause the video, give the problems a try, and then when you come back, I'll have solutions for you. These are the solutions to the 3 problems. When I was an undergraduate, I didn't really like this topic so much. I'm not sure why. Maybe if they had called it like force fields or something, maybe I would have thought that was more exciting. But now I really like this because I think it seems very dynamic and things are happening, things are in motion. And also probably it helps that no one's grading me on my understanding anymore, but I actually like it. It's a nice, it seems very practical. It comes in engineering. And as I said, I kind of like the little drawings. And I used to not like it. I think one of the things I didn't like as an undergraduate is you would draw these vectors and then you would move them around, and it seemed very chaotic to me. But actually, when you draw, after you've drawn a couple, like if you try drawing this one here, and you try drawing a couple, maybe even this one, you actually start to get used to it, and it doesn't seem so bad. So maybe if you do a bit more practice, hopefully you'll come to like it like I do. I'll just wish you luck with that. And that is it for this video. Thank you for watching.